Good morning. Welcome to session one of sweep frequency response analysis. So this will be at least 3 sessions long, possibly 4 sessions long, to talk about how we utilize sweep frequency response in respect to transformer testing. So we're going to have to go through some basic principles, but when we talk about sweep frequency response analysis, we're actually talking about sending a signal into the transformer in various configurations and then receiving that signal and monitoring the difference between the input and the output that we just received, what we sent in and what we received out. So to begin to understand why we're actually doing this, we need to have a quick review of the reaction of resistive, inductive and capacitive portions of a circuit. So let's go back to that. So we talk about impedances, okay, and that would be in ohms. And so we have the values of the impedance, capacitive reactance, the impedance of an inductor, inductive reactance, and they're both a function of the frequency. And so capacitive reactance is this equation. It's one of the needed two, needed three questions. 1 over 2 pi f c, where f is frequency, c is capacitance in farads, and when we talk about inductance, L is in henries. So, and another thing to remember is it's this little combination of 2 pi, 2 times 3.14 is 6.28. We can remember that. So if we look at a brief review of this, if we look at the capacitive reactance of a circuit, X sub C, 1 over 2 pi F C. Okay, so let's look at what happens when frequency goes up and frequency goes down. What happens to X sub C? Well, if we look at the equation here, we can see as frequency goes up, the denominator gets larger. So X sub C gets smaller and smaller. 1 divided by a larger number gets smaller and smaller. So X sub C would go down and down and down. As a matter of fact, as the frequency got really, really, really large, then this X sub C could approach 0. Now, as frequency decreases, this denominator gets smaller and smaller and smaller. At some point, it gets really large for the total inductive or capacitive reactance. So the capacitive reactance gets larger, and it could approach infinity. And it's going to approach infinity when the frequency gets down towards 0, because 1 divided by something close to 0 is going to be infinite. So let's look what happens to X sub L when this is going on. X sub L is basically 2 pi FL. So as the frequency goes up, what happens? And as the frequency goes down, what happens? Well, X sub L, it's all one line here. As the frequency goes up, X sub L is going to go up. As the frequency goes down, X sub L is going to go down. So we can see the impacts of frequency on the capacitive reactance and inductive reactance of the circuit. Now, what happens to R? R is R and is independent totally of the frequency at all times. So it stays the same. So let's look at this network. Like I said, we're going to have an input and we're going to have an output. And so when we look at this input, this is the input here, and this would be our test set where we're actually providing a signal, some sort of sinusoidal wave. And here's our output where we're actually going to receive this and monitor it. So we don't know what's inside here. In our case, what's inside here is a transformer and all the various components of that transformer. So we're going to look at that. So let's look at this resistance, just to go over things quickly. If I've got a resistor of 50 ohms, then it's going to be 50 ohms all the way through all the various frequencies that I might have here. So it has no impact on that whatsoever, because it's not dependent on frequency in any way. So to summarize again, Now I've got a capacitor here, 1 over 2 pi FC, okay? And I've got 20 microfarads. So if I do the equation here, and at 0 frequency, this X sub C right here, it's going to be what? At 0 hertz, frequency is 0, it's going to be infinite, okay? Well, at 60 hertz, I've got 6.28 times 60 hertz times 20 microfarads, and do the inverse of that. I've got 132.7 ohms. Let's go on down here and try to do 10,000 hertz, okay? Okay, so 6.28 times 20 microfarads times 1,000. It's 1.25 times 10 to the 11th. So it just keeps getting bigger and bigger. Let's review this number here to make sure I did it right. So 6.28 times 20 microfarads times 60, and 1 over that. Yep, 132.7 ohms. So you can see how it would increase with time and the frequency. So let's look at the capacitor. Got a 3 millihenry capacitor here. And basically, what's X sub L? Well, X sub L is going to increase with frequency. At 0, it's going to be 0 ohms. But at 60 hertz, 2 times pi, which is 6.28, times 60 hertz times 3 millihenries is 1.13, according to my calculator, if I can read it right here. And over here can be 10,000 times 6.28 times 3 millihenries is going to be 188. So you can see it's going to increase with time. So we can get the feeling of what we're doing there on each one of those. So what we're actually going to do is we're going to monitor what comes in versus what comes out. So looking at the output, V out over V in, and we're going to use this function called log to the base 10, and we're going to get an answer in decibels, dB. So back in my college days, we had to design some amplifiers because we wanted the output signal to be larger than the input. We're trying to amplify our signal so we can hear it on a set of speakers. So we would do that, and we would do the calculation V out over V in. So let's simple chart here. And so let's just say that we had 10 volts input, and I got 100 volts out. That would be 100 divided by 10, be 10. And so I've got that going on. I've got 10. But now if I use the log function, 20 times the log of 10 would be 20 dB, because the log of 10 is 1. So I can go through the chart here and find out that if I got exactly the same output as I've got as the input, I would have 0 dBs. If I have 1/10 the output of what I had for the input, it would be minus 20 dB. 1/100th is minus 40 dB. So I hope you can see the pattern here is that every time I go down by a value of 10, like 10 to 1 to 1/10 to 100th to 1,000th, I go down 20 dBs. Okay, so each drop of 20 dB corresponds to 0.1 of the previous number. Okay. And we can do some of those things as well. So if I have an input here, and here's my in, and here's my out, and my input is 10 volts, and my output is 5 volts, then basically V out over V in is 5 over 10 is equal to 0.5. So if I look at the actual gain, it would be 20 times log base 10 of 0.5. And when I do that number, 0.5 log times 20, I'm going to get minus 6 dB gain. So my output would be a minus 0.6 dB. All right, enough of that. Let's look at the basic resistor. So if I'm putting the signal in here on my input, and here's my output, I'm trying to complete that circuit. So it's more than just a meter that I've got here. I'm putting an input in, and I'm actually providing, there's my two-port network, which has to be a resistor. I'm actually providing a path for it to return back. So here's my input, there's my resistor. My losses are across this resistor, but it really doesn't matter what the frequency is. If I vary the frequency from 0 hertz up to 10 times 10 to the hertz, or from 1 hertz up to 10 times 10 to the hertz, this is a flat line. My output is going to be the same across everything because the resistance, the reactance of that resistor doesn't change with resistance. Now, look at the ideal inductor. We know that some things happen. So look at 2 pi FL, the impedance is going to go up with frequency. So what happens when the impedance goes up? Frequency got bigger here. So the impedance went up. So I've got more and more losses dropped across that. So it started out to where, okay, it was at 0 hertz. This was a short circuit. But then I had losses because the impedance got bigger and bigger. So it's a dead short at low frequencies, and it's an open circuit at the higher frequencies. What about the capacitor? Well, the capacitor is just the opposite. It's an open circuit at lower frequencies, and it's a short circuit at higher frequencies. So at very low frequencies, I get nothing output. But as the frequency increases, the impedance across that capacitor gets less and less until it's basically a short circuit. So that would be the response that I would see for that capacitor with an input and an output. Again, I'm pushing in the signal and I'm completing the circuit with my receiving end of the test set. So let's talk about a few things. Tuned circuits. So we had a brief review of what happens to capacitive reactance and what happens to inductive reactance. We had a brief review of that, but let's look at this tuned circuit. We have a frequency here at which the inductance and the capacitance X sub L equals X sub C. Now there's a derivation, so you can actually come up with this equation that, again, is a neat question. But frequency, inductance in henries, capacitance in farads, always 2 pi 06.28. So basically the point at which X sub L equals X sub C is called resonance. And so we need to understand what this whole concept of resonance is. So if I look at this very simple basic circuit where I have some signal coming in and I have a resistor and I have a capacitor and I have an inductor here, it's all right there. Let's say that the frequency is at this point. Remember, the resonant frequency is what? 1 over 2 pi square root of LC. So let's just say that the frequency is where these 2 points are equal together, and that's the frequency I'm operating right now. And so it turns out that at that frequency, in this case, the capacitive reactance equals the inductive reactance equals 4 ohms. Well, if you've taken some of my math classes, that's okay if you haven't, but brief little review, that the total impedance of this circuit, Z total, is going to be the resistance plus X sub C plus X sub L. Well, X sub C is not just ohms, it's at an angle. So when I look at this, this is going to be some resistance, which is resistance plus J0, looking at rectangular pole components, plus the capacitive reactance, which is going to be 0 minus J4, means that it's down here. And then plus the inductive reactance is 0 plus J4, that we can find that for this series circuit at the resonant frequency, this minus J4 and this plus J4, they cancel each other out. So the total impedance of this circuit at resonance is that value R. So basically, at resonance of a series circuit, the capacitor and the inductor are just a short circuit. You can eliminate them. So the only thing in that circuit effectively would be that resistance. Now, if I look at that series resistance, the whole review of it, so looking at it again, what happens is we can get a better picture of it here. It's like, here is a graph of what happens to this X sub L right here. As the frequency goes up, the impedance goes up. So I can see X sub L going up. If I look at X sub C, that's right here. It's the equation is 1 over 2 pi FC. As the frequency goes up, it gets smaller and smaller. So basically what I've got is I've got X sub L going like this, and I've got this going like this. Okay, and so this point in the middle is the resonant frequency. So if I look at it and just do a graph of Z total, the total impedance of the circuit, at this point, the resonant frequency, all I've got is the resistor there. So that reinforces what we did in the previous slide. So effects of capacitors and inductors and resistors, this curve, the sharpness to it, how quick the slope is, has a function of capacitive with respect to inductive with respect to capacitive, and how small the resistance is. So the smaller the resistance is, and knowing here I'm monitoring current, I have a large current flow. So I can see that I can vary the shape of that by having various ratios of inductance to capacitance, okay? So I can see that I can have various shapes in my response curve. Now, parallel resonance. Let's just say that X sub C equals X sub L, 4 ohms again. Well, I have to go back and understand that if I look at just that portion of the circuit, that parallel portion of the circuit, that's the product over the sum. So that would be what? That would be X sub L times X sub C divided by X sub L plus X sub C. So I can do that, but I have to go back to my mathematical classes. But let's just look again at X sub L plus X sub C. That's going to be 0 plus J4 plus 0 minus J4. And look, I got a plus J4 and a minus J4 in the denominator. I got a 0 in the denominator. So I've got some number up here divided by 0. That's basically undefined, but in my world, that's infinitely large. So at resonant frequency for this parallel circuit, that becomes an open circuit. And so the only thing left in the circuit, again, is R. So it's a little odd that you just see in both cases, R is all that's left. So how does that impact us? Again, we've got some curves here that show how that we can change the peak and the width of that resonance that we monitor, and the effects that we have with resistance as compared to the various ratios of capacitive and inductance. So just a couple real quick problems here that we can look at that will help us maybe. Let's just say that I've got this circuit right here. So I got 4 ohms. It's like, find the resonance, find L if the resonance is 1800 hertz, okay? So I have to use that equation. Frequency equals 1 over 2 pi LC, square root of LC, okay? And I'm going to go through this pretty quickly, but the frequency is equal to 1800. is equal to 1 over 2 pi square root of, and I don't know what L is, but I do know that the capacitance is 2 times 10 to the minus 6th. Well, I can do some math there, and I can figure out and multiply both sides. So I'm going to multiply this over. I'm going to get the square root of L times 2 times 10 to the minus 6th is going to be equal to 1 over 2 pi times 1800. Little quick algebra there. So if I do all this math, I square both sides and then divide through. So I'm going to square both sides. I'm going to get L times 2 times 10 to the minus 6th equals 1 over 2 pi, 1800. And I have to square that. And then I divide by, I can solve this and find out that this L happens to be 3.9 millihenries. So you can do that math on your own. Then the question number 2 is find x sub L and x sub C. Well, I'm just going to find x sub L is equal to x sub C is equal to 2 pi FL. And so 2 pi FL, 2 times pi, and in this case was 1800 hertz, times 3.9 millihenries. And when I do the math, I find out that basically the impedance is 44 ohms. Okay. And in question number 3 is a question that I could have answered without looking at anything else in this problem, because current is equal to voltage divided by impedance. And in this series circuit, remember, it's a short circuit at resonance. It's just going to be 20 volts divided by 4.7 ohms. Resistance is all I've got, and that's 4.26 amps. Pretty basic. Now, what happens in this parallel resonance circuit? It doesn't change a whole lot. What's the resonant frequency? Well, resonant frequency is 1 over 2 pi square root of LC, 1 over 2 pi square root of 0.1 times 10 to the minus 3 times 10 times 10 to the minus 9th. So we can do both of those things, and we can come up with the number. And if I go through the math there, the resonant frequency is going to be equal to 160 kilohertz. It's going to be pretty large. And I've got that. Okay. So what's the value here? Well, I don't even really need to calculate the value, because at resonant frequency, what happened? This is an open circuit. Open circuit. So what's the value of VC at resonance? Well, this is a parallel circuit, and this is open circuit. So at resonance, voltage across the resistor is equal to voltage across the capacitor is equal to voltage across the inductor, equals 2 milliamps times 2,000 ohms, because that's what I've got here. It's 4 volts. So I've got 4 volts across everything here. Now here's the amazing thing I want you to see. And I'm not going to go through all the math here, but it's an amazing thing. I've got 2 milliamps of current flowing right through here. Okay? Which means by Kirchhoff's current law, 2 milliamps here, the current flowing down this part of the circuit has to be 0 milliamps, because it all flows through this 2K ohm resistor. But that doesn't make sense, because I've got 4 volts across that resistor. So I've got to have 4 volts across here and 4 volts across there. And I do. So even though I've got 0 current flowing through here, I've got some current flowing in this inductor and this capacitor. When I do the math, I find out that these components, x sub L equals x sub C, it's about 100 ohms. So I've got 4 volts divided by 100 ohms is what? 4 milliamps. Yeah. Or 0.04 amps, right? Do the math. Can't even think in my head this morning. 0.04, yeah, 0.04 amps. But what's happening in this circuit is in this little capacitor reactor circuit, I've got 4 or 0.04 milliamps circulating in here, but it's going this way, and then it's going this way, and then half the cycle is going back this way and half this way, and I have no current flowing in. So it's an amazing thing it's called a tank circuit. It just dies right there. But there is current flowing back and forth between those two components. But the sum of those two currents is basically zero in heaven, as long as it's pure capacitance and pure inductance. So let's look at the frequency responses here. Trying to close this thing up. If I look at the frequency response of this circuit, here's my input, and here's my output. Remember, I'm just trying to complete this circuit and bring it back to the source. I've got a resistor, I've got an inductor, and I got a capacitor. Well, here's my gain out here. At resonance, remember, at resonance, this is a short circuit. At resonance, all I have is resistance, so that could be close to 0 dB. No losses, no gains. But as I look here, at very low frequencies, my capacitance is large. So I'm losing a lot of the signal right here. That's my capacitive portion. And at very high frequencies, the capacitance is small, so it doesn't matter. But at very high frequencies, the inductance is large. So I would have more losses. So as things change, my output will change. So at this resonance, I will see a peak. Now, if I look at a tank circuit, and I look at this at very low frequencies, the inductance is very small. So basically, this would be my path. Right there it is, 0 dB. I'd have no loss. At resonance, these two guys are an open circuit, and so it's just purely resistance. And when I look at the other side of it, the capacitive response at high frequencies, it's pretty small, so I will get back up to here. So this would be my response circuit for trying to get through that tank circuit. Okay, again, nothing can get through the tank circuit at resonance. It's a very high impedance, so I'd have a lot of losses right there. So we look at this, the summary of RLC networks. At resonance, we'll either have a peak or a valley, and it's going to be created by that combination of inductance and capacitance. Since inductance and capacitance are dependent upon geometry, basically the thing is like I'm having, when you look at a capacitor, it's two plates. How close are they next to each other? How big are they? Those sorts of things. If things change there, then I will have a change in the output. And changing R only impacts the size of the resistance, and that's it. So let's look at the basic transformer here. So the basic idea behind frequency response. If I look at the measurements here to evaluate, so this would be the high voltage winding of my transformer, or high voltage bushing. There's my low voltage bushing. And so inside that transformer, I've got all kinds of inductors and resistors and capacitors between the layers of everything. So if I were going to lay it out and actually look at a diagram, I could see, right here's a capacitance that I have between turn to turn, one piece of wire laying next to another piece of wire with insulation between is going to be a capacitor. Then I've got capacitor here from low voltage to high voltage. That's from one side to the high side. Then I've got a capacitor here between each layer of the winding. And then I'm going to have resistance and inductance in the actual copper winding itself. So I have all those components. And then I go to what? Another layer right here. So if I look at the whole scheme of things, I've got lots of capacitors and inductors. So this would be my diagram. And here would be my high voltage winding that I've come in. There's my low voltage output coming right there. And I can see that I've got capacitors, inductors, and resistors. I've got clamping here that impacts things. I've got a core here. There's the area between the various layers. There's some other clamping. There's the next phase. It is an immense network of combinations of resistors and capacitors. Now, if I put my signal here and I try to respond and look at it back here, let's just look at some things. So if I look at a path for DC and very low frequencies, I have to remember 1 over 2 pi FC or 2 pi FL. Low frequencies, this is the guy. Inductors and resistors. At low frequencies, this would be very high, very high. X of C is very high. So any capacitance, I wouldn't want current flowing through. It can't go there. So I'm going to see this, and at 0 DC, at DC, I'm going to see that, you know what? This is going to be basically 0 ohms. So basically, those inductors just disappear. And so at very low frequencies, all I'm going to see are the resistors going through this network. So the path would be like this. And so my output would be my Vin, and there's my frequency. It's going to be the same all the way through. That kind of makes sense. Now, as I increase the signal, and now I've got a sinusoid here, again, but it's low frequency. So that's 2 pi FL and R and 1 over 2 pi FC. I still don't want to make any paths through the capacitors. So I'm not going to do the capacitors because they are very large. X sub C is big, big, big. So the path would be through the actual inductors and the resistors there. And I can follow that path through. Now, at very high frequencies, go back again. R is always R. X sub L is 2 pi FL. X sub C is 1 over 2 pi FC. So at very high frequencies, this guy is big, 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 big. So I won't pass through any of those inductors, only through the capacitances. And I can see my path now that the signal would go through, shown in red on this diagram. Looks pretty impressive. Those are the capacitive, inductive, and resistive circuits. So that's a pretty quick review of what we're going through on the sweep frequency response analysis. Hopefully it was understandable to you. And if you have questions, let me know. But please email me to let me know that you have actually completed this so that I can record it in our attendance. I appreciate your listening to the audio today. Take care, and session 2 will be coming out next week.